Now let us account for excess loss in the calculation of the tap port and throughput port losses. So it's not, since we have an excess loss, it's not an ideal directional coupler anymore. Therefore, P2 plus P3 will not add up to P1. Okay, so we will start with the definition of the excess loss given on the previous slide. Excess loss is by definition minus 10 times logarithm of P2 plus P3 divided by P1. This expression inside the logarithm we will rewrite. We will take P2 over P1 outside the square brackets. Inside we will have 1 plus P3 divided by P2. And then we have here two terms, product of two terms, and by the property of the logarithm, that the logarithm of the product is the sum of two logarithms, we will have two logarithms, right? From the first term, from this one, we will have minus 10 times log P2 divided by P1, and from the second one, this one, we will have minus 10 times log of P2 plus P3 divided by P2. Now, this term, let me highlight it, let me remove my highlighted here. So this term is by definition the throughput port, and therefore we will rewrite it. Instead of this expression, we will plug in throughput port and solve this equation for the throughput port loss. Therefore, the throughput port loss will be excess loss minus this term, right? 10 times log of P2 divided by the sum of P2 plus P3. We can take P2 over P3 inside the logarithm. We can take P2 over P3 outside the square brackets to have P2 over P3 plus 1 left inside the brackets. And the last step, this last term under the logarithm, we can rewrite as P2 plus P3 divided by P3. Okay, now looking at this expression, let me remove the rest and focus on this expression. So if we have an ideal case, for example, which is not the current case, but let us assume that we have an ideal case. For an ideal case, P2 plus P3 equals P1. And if P2 plus P3 equals P1, we will have here P1, so P3 will cancel. We would have here expression minus 10 times log of P2 divided by P1. And we will define this term as throughput loss, but we will put mark. Okay, so throughput port loss prime. And as a result, we will have a simplified expression, right? That the real throughput port loss, that is the loss when we have internal losses and not zero excess loss. So for real coupler, the throughput port loss equals excess loss plus the throughput loss for an ideal coupler. Okay, so ideal L prime is the throughput loss when there are no excess losses, but the splitting ratio remains the same. In a similar manner, we can also calculate a tap loss for real coupler with an excess losses. I will skip this discussion and will go directly to the result on the next slide, but you can easily recreate these calculations yourself. So in a similar manner how we calculated the real throughput loss, we will get a similar result for real tap loss. So real tap loss meaning that the loss for the directional coupler with non-zero access loss will be equal to access loss plus the coupler loss, tap loss for an ideal coupler. And let us summarize those results on the next slide. When the losses are present in the coupler, that is, when the excess losses are not zero, the actual throughput loss is an ideal throughput loss plus excess loss, and the real tap losses, ideal tap losses, plus excess losses, which is actually very convenient and simple to use. I just want to mention here that the directional coupler is normally a symmetrical device. That is, we discussed so far that we use port 1 for input and port 2 and 3 for throughput and tap output ports. But if we flip the situation, for example, and send light to port 2, will this directional coupler work? And the answer is yes. But in this case, let's say if we send light to port 2, then port 2 will become port 1, port 1 will become port 2, port 4 will become port 3, and port 3 will become port 4. And normally the splitting ratios and all the losses will remain the same as for the reverse situation. With this in mind, let us build a duplexing network using two directional couplers. Duplexing means simultaneous transmission in both directions through the same fiber. As you can see here, we have a fiber, then two directional couplers, and two users. One user on the left that can transmit and receive signal through two ports, and another user is on the right that also can transmit and receive signal using two other ports. Two directional couplers are in use. For directional coupler 1, we do not use this port. So we do not use this port, so it's redundant. And also for second directional coupler, we do not use this port. But other than that, we indeed can build duplexing network. For example, transmitter, let me change to the pointer. Transmitter here, we can use port 1 for the light to enter the directional coupler, and then light will go through throughput port 2 of the first directional coupler, and then enter first port of the second directional coupler, and will be split between port 2 and port 3 of the second directional coupler. The throughput port will go here, and the port will go to the receiver. And in fact, for the transmission part from the first user to the second user, we use the tap port. And situation is symmetrical when we transmit from the right to the left. Example. Let us compute the transmissional loss assuming ideal 3 dB couplers. Remember, ideal 3 dB couplers is when the splitting ratio is 1:1, and the port losses for throughput and tap ports are the same, 3 dB. So if we transmit it from the left to the right, we will have first loss 3 dB through first ideal directional coupler, and then another loss 3 dB through second directional coupler. Overall, when the signal propagates through, let me change it to the marker, from this transmitter on the left to the receiver on the right using this path, total loss is 6 dB. Let us a little bit complicate our task. For the same duplex network, let us compute losses assuming that in this case we have the same 3 dB coupler, but they are not ideal. The excess loss is 1.5 dB. In addition, we have 4 connectors connecting fiber to directional couplers and to transmitters and receivers with 1 dB loss per connector, and also overall we lose 2 dB inside the fiber. With this in mind, overall transmission loss, so it will be losses through the first directional coupler, it will be ideal loss 3 dB plus 1.5 dB excess loss. So this is, I will change it to marker, this is the loss first directional coupler. That's how much signal goes to port 2 of the first directional coupler. And then those are losses through the second directional coupler. That's how much signal will go through the port 3 of the second directional coupler. Plus we have 4 connectors, 1 dB per connector, total 4 dB loss for connector and 2 dB loss for the fiber. Adding it up, we will have 4.5 dB plus 4.5 dB plus 4 plus 2 dB. We have losses 15 dB. Compare it with the previous slide where we have idealized case and total losses are only 6 dB. In reality, we have to account for couplers, fibers and excess losses, and losses could be substantially higher. That is all for this lecture.